Thermodynamics is like a universal recipe book for the cosmos. It helps us understand how energy transforms and flows in natural processes. From the engine of your car to the heart of a star, thermodynamics governs it all. It helps us design engines, predict weather patterns, and even understand the evolution of the universe. Imagine a world without thermodynamics. We wouldn't have refrigerators to keep our food fresh or power plants to generate electricity. Transportation would be a challenge without the internal combustion engine, a testament to thermodynamic principles. Thermodynamics isn't just about complex machines, it's about understanding the fundamental laws that govern our universe. It's a journey into the heart of energy, its transformations, and how it shapes the world around us. In thermodynamics, we talk about systems. A system is simply the part of the universe we're interested in. Imagine a cup of hot coffee, that's our system. There are three types of systems. An open system can exchange both energy and matter with its surroundings. Think of a boiling pot of water. A closed system can exchange energy, but not matter. A tightly sealed bottle of water is a good example. An isolated system can't exchange energy or matter with its surroundings. A thermos flask tries to approximate this. Understanding these systems is crucial because it helps us define the boundaries of what we're studying. It allows us to analyze how energy interacts with matter in a controlled manner. The Zeroth law of thermodynamics might seem obvious, but it's the bedrock of temperature measurement. It states that two systems in thermal equilibrium with a third system are in thermal equilibrium with each other. Think of thermometers. When you place a thermometer in a cup of hot water, heat flows from the water to the thermometer until they reach the same temperature. This is thermal equilibrium. The Zeroth law ensures that all systems, after reaching thermal equilibrium, have a consistent temperature. This consistency is what allows us to use thermometers reliably to measure temperature. The first law of thermodynamics is a grand statement about energy. It can neither be created nor destroyed, only transformed from one form to another. This is also known as the law of energy conservation. Mathematically, the first law is expressed as delta U equals Q minus W, where delta U is the change in internal energy of the system, Q is the heat added to the system, and W is the work done by the system. This law governs everything, from the expansion of gases in engines to the energy flow in biological systems. It's a cornerstone of our understanding of how energy functions in the universe. Section 5. Work and heat, two forms of energy transfer. The first law introduces us to two important concepts, work and heat. Work is the energy transfer associated with a force moving an object over a distance. Think of pushing a box across the floor. You're doing work. Heat, on the other hand, is the energy transfer driven by a temperature difference. Imagine holding a cup of hot coffee. Heat flows from the coffee to your hand, warming it up. Both work and heat are ways energy moves between systems, but they differ in their mechanisms and effects. Understanding this distinction is key to grasping many thermodynamic processes. Section 6. Specific heat and its significance. Have you ever noticed that some materials heat up faster than others? That's because of a property called specific heat capacity. It's the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Water, for instance, has a high specific heat capacity, meaning it takes a lot of heat to raise its temperature. This is why oceans moderate Earth's climate. Specific heat capacity is crucial in many applications. From designing efficient cooking utensils to understanding heat transfer in buildings, it plays a vital role. Section 7. The second law of thermodynamics, entropy and irreversibility. The second law of thermodynamics tells us that the entropy of the universe always increases over time. Entropy is a measure of disorder or randomness. The more entropy, the more disordered a system is. Think of a deck of cards. A new deck is highly ordered or low entropy. Shuffle it, and the order breaks down, increasing entropy. The second law says that natural processes tend towards disorder. The second law has profound implications. It tells us that some processes are irreversible and that there's a directionality to natural events. It's a fundamental principle governing the evolution of the universe. Section 8. Entropy, a measure of disorder. Entropy, often described as a measure of disorder, is a central concept in thermodynamics. It quantifies the number of possible microscopic arrangements within a system that correspond to its macroscopic state. Imagine a room with toys scattered all over. This disordered state has high entropy because there are many possible arrangements of the toys. Tidying up the room reduces entropy because the toys are now in a more ordered state. Understanding entropy helps us predict the spontaneity of processes. Systems tend to evolve towards states of higher entropy, reflecting the universe's inclination toward disorder. Section 9, Reversible and Irreversible Processes. The second law also introduces the concept of reversible and irreversible processes. A reversible process is one that can be reversed without any net change in the system or its surroundings. This is an idealized concept rarely found in reality. Irreversible processes, on the other hand, are those that leave a permanent change on the system or its surroundings. Most real-world processes fall into this category. The distinction between reversible and irreversible processes is crucial in understanding the efficiency of engines and the limitations of thermodynamic cycles. Section 10, the Carnot cycle, an ideal engine. The Carnot cycle is a theoretical thermodynamic cycle that represents the most efficient engine possible. It consists of 4 reversible processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. While no real engine can achieve the Carnot efficiency, the Carnot cycle serves as a benchmark for comparing the performance of real engines. The Carnot cycle highlights the key factors influencing engine efficiency, such as temperature differences and the nature of the working substance. Section 11, the third law and absolute zero. The third law of thermodynamics states that the entropy of a perfect crystal approaches zero as the temperature approaches absolute zero, 0 Kelvin or minus 273.15 degrees Celsius. Absolute zero is the lowest possible temperature, where all molecular motion ceases. The third law has profound implications for the behavior of matter at extremely low temperatures. It explains why certain materials exhibit unusual properties like superconductivity and superfluidity. The pursuit of absolute zero has been a driving force in scientific research, leading to discoveries that have revolutionized our understanding of matter and the universe.